Okay, so this morning we have Charlie Elliott from the great Applied Mathematics Center of Warwick, which of course has a huge tradition in dynamical systems and PDEs. And he's going to be talking about a theme that I guess is very close to the hearts of quite a few people, namely PDEs on evolving domains. We've heard a lot about issues of dilution, advection, and so on, so it'll be great to hear more.
Okay, so it's been a pleasure to take part in this workshop, though it's stretched me quite considerably last week, I have to say, but it's always good to be stretched, listening to things that you haven't heard before, and also listening to talks from people whose experience means that they have different ways of thinking, and that always subconsciously affects the way that they talk. And I'll ask you to forgive me in the way that I've been accustomed to speak to analysts, applied analysts and numerical analysts, and sometimes to physicists. So there'll be hidden things which I'm unaware of. So forgive me for that. I'm a mathematician. I'm not a physicist. I'm not a biologist. So I'm not going to tell you anything about biology. I'm not going to tell you anything about modeling very much. I'm going to say some things about how one might approach the problem of looking at partial differential equations on holding in regions of space which are changing in time. And that's what we mean by evolving domains. So the domain is a region in space, it's time dependent, and it changes. And we want to solve a partial differential equation on that region. Of course, in some sense, the first thing you have to do is to say what you mean by an evolving domain. And of course, really the first thing you have to do is to say what you mean by a domain. If you don't know what you mean by a domain, then you will not be able to write down a mathematical description of it. Well, you have to write down a mathematical description of it, and that's the first step in writing down a numerical method or a discretization. So you have to have a definition. That's just the way that it is. So that's mathematics. So mathematics is you have to start with definition. So that will influences a little bit the way that I'm going to give this talk. And I'm at the University of Warwick. A lot of this work started when I was at the University of Sussex, which is now the home of Anatida and other young numerical mathematicians and applied analysts, where there's a lot of work done on mathematical modeling in biology and partial differential equations. Some of this work here started then. In particular, my interest in solving partial differential equations on evolving domains by the method that I want to talk about today began in 2003 when I was at this institute here. I was the principal organizer of a program, Computational Challenges in Partial Differential Equations. Previously to that, I'd been very much interested in phase field models for approximating surface flows, for approximating surface evolution. We saw a talk on phase field yesterday. So I spent a lot of time working on Cahn-Hilliard equations and generalized phase field equations for the approximation of curvature-driven flow, and I thought phase fields were the B's and E's, and meanwhile my colleague Gerd Zuck from Freiburg, who a long time ago in the 80s, he decided that it would be quite, because his background was geometric analysis. So Gerd Zuck, his background was geometric analysis. He began studying differential geometry with analysis in Bonn. Then he turned to applied mathematics because he realized that computing things was important in applications, and computing things was important in differential geometry, to give people pictures of things that they can only imagine in their mind. So one of the things that he thought would be interesting to do was to solve the Poisson equation on a curved surface. So he took the step from solving the Poisson equation on a flat domain. By a flat domain, I mean that you're living in a space where the description of the space is such that the normal is constant. And that's what we normally do. And most of the talks that we've seen, in fact, almost all the talks we've seen, when they've talked about solving partial differential equations, they've spoken about solving partial differential equations in flat domains. Anyway, he decided it would be interesting to look at numerical methods for solving Poisson equations in curved space. That basically means solving the Poisson equation on the surface of a ball, on a sphere. And rather than writing down a parameterization, which you can do, well, of course you can always write that down using spherical polar coordinates. Everything is hunky, you're in a square domain, but if you do that, you'll find that there are artificial things you've introduced. You've introduced an artificial singularity into the differential equation. Completely artificial. It's got nothing to do with it. It's because of your chosen parameterization. So rather than doing that, it's natural to think of discretizing the surface of the ball. And if you're working with finite elements, it means that well, in the usual finite element, you have a domain in usual Cartesian domain. Suppose that it's a cube. You divide the cube up into smaller cubes, and you divide each small cube up into tetrahedra. Each tetrahedron is a finite element, if you like. These are flat tetrahedra. So his idea was that you discretize the surface of a ball by triangles. So now your triangulation it's now an interpolation of the sphere, and you put your numerical method onto the surface of the sphere, and so that's what he did. And and he then went on to think about evolving these surfaces. And because his background was geometry, geometric analysis, he looked at the standard geometric flows. The standard one is motion by mean curvature. It's where you say that the normal of the normal velocity of a surface is given by the mean curvature, and that's a gradient flow for minimizing the area. If you're given a surface and you want to reduce its area fastest using steepest descent, then you're led to the evolution equation. Normal velocity is equal to minus the mean curvature. That's a geometric partial differential equation. If you look at it in the right way, it looks a bit like the heat equation. So now he derived a numerical method for solving motion by mean curvature using triangulated surfaces. So here the idea is that you've got your surface as a union of triangles. Think of a closed surface, a union of triangles. And you have to find the location of the vertices of the triangles. And you have a discretization of the equation somehow. And what you compute is the location of the vertices of the triangles. And that's basically the surface finite element method.
There's a very beautiful software package that does precisely that, using adaptive mesh called Surface Evolver.
Surface Evolver is a kind of a strange animal which existed, this was developed by Bracker, and it doesn't have the same status with respect to the discretization of partial differential equations as the method that I'm going to, as what I would like to talk about, though I will not be able to say very much about it in this lecture. So in 2003, Good and I had been talking about these kind of problems for a long time, and we'd collaborated on certain things, and we had a project in which we were going to write a review article which was supposed to turn into a book about methods for solving geometric partial differential equations. and I was going to be responsible for phase field and level set. But meanwhile, when we came to Cambridge, we thought it would be interesting to look at partial differential equations holding on these evolving surfaces. So now we're moving from a partial differential equation holding on a stationary surface to a partial differential equation holding on an evolving surface. So we started that work in 2003, and in increments over the years we've effectively had basically the numerical analysis in 2003, and we've gradually improved it, and it's gone on in a number of different directions. So that's without whom this would not be possible. The first person is Gerd Zook. Gerd is now retired, but I'm trying to bring him back occasionally into doing mathematics. Amal Alphonse is a current PhD student of mine. He's writing his thesis at the moment, and he's always resisted doing numerical analysis. I mean, he's certainly resisted doing numerical methods and implementing things, but he's actually resisted doing the mathematical analysis for discretization. But what we've done here is to, with Amal, is to develop a more abstract way of thinking about PDEs on evolving surfaces, which I'll give you a little bit of a flavor for in this talk, but I think it's way out of, to do it properly, I would have to do some mathematics, which is not possible to this audience in the short period of time that I have. But I will show you bits and pieces of it, so you can think, oh, I don't want to do that. Okay? So this is Hans Fritz is a current postdoc of mine. He's a research fellow funded by the Humboldt Foundation. He has what's called a Fyodor Leinen Fellowship. He is the penultimate PhD student of Gerd Zook. He's going to Regensburg in January. With him, I've been looking at a way of generating good meshes. So you'll see in a moment why that's important. So here we have a mathematical way of solving PDEs to generate the mesh. Tom Ranner is an old PhD student of mine. With him, I'm trying to tie up lots and lots of things together based upon the abstract framework with Amal on the finite element analysis. And basically, the end of the day, we have an abstract formulation of a parabolic equation in an evolving space, and the abstract analysis includes PDEs on evolving flat domains, evolving curved domains, and allows solving coupled surface bulk equations on in evolving domains in the same equation. And as we do the same numerical analysis, the method is the same abstractly. You just have to test whether your numerical method satisfies the abstract assumptions. With Bjorn Stinner, he was a postdoc of mine. Tom Ranner is now a postdoc in Leeds. Bjorn Stinner is a colleague of mine in Warwick. He was here last week, and he's going to be part of this program. And we've done work jointly with Amal, but we did some work on what I call geometric biomembranes, which I hope to discuss a little bit. Chandrasekhar Venkataraman, he's here at the back. He was a postdoc of mine, and we did a certain amount of work on some parameter identification on models for cell motility, which appeared in the kind of mathematical computational biology literature. And we've also done some numerical analysis on what we call the ALE method, ALE approach to evolving surface finite element method. Okay, so Shekhar's going to be here, or the program. Bjorn's going to be here on and off for the next few months. Tom Ranner is going to be here in September for a short while. Hans Fritz is going to be here in September for a short while. Of course, PDEs in evolving domains they occur all over the place. They occur in fluids, as we saw yesterday. They occur in biology. They occur in material science. And they also, surface PDEs also occur in imaging and segmentation and certain types of inverse problems. If you want to recover a surface, an interface of discontinuity, where say the diffusion coefficient changes across the surface, and you have data, then you will eventually a numerical and a mathematical approach to this will be to find the surface, and if you use standard inverse methods and then minimize your objective functional, you will eventually be led to that interface changing in time, and you'll be led to a surface PDE. So you may not want to use it by solve it using surface finite elements. You may be led to using phase field. So surface PDEs, PDEs in domains which change, they occur in many different circumstances. And this was a compelling, compelling pictures from what giant unilamellar vesicles, which are created in the laboratory, and they're compelling to mathematicians because you can see, without knowing anything, that this is associated with energetic surfaces. This is why you get spheres. You can see that there's quite likely to be some kind of phase separation, and so you can easily think of a mathematical model for this. But you also see that this thing is complicated in some sense. You also see they're going to have to solve problems on curved domains. These are the things, in 2003, I was looking at all sorts of literature, and I could see that the necessity for solving partial differential equations on domains which change in time and on surfaces was important. I'm not a biologist, but I could see that if you actually were going to be doing anything in cell biology, which is approaching what people can do in material science, that you're going to have to face this problem. So it's clear that there was an opportunity to do some mathematical and numerical analysis, irrespective of the mathematical modeling. Okay, so this is going to be useful. Irrespective of the mathematical modeling, looking at PDEs on evolving domains is going to be useful. And you see that you've got complications. You can see there's geometries. And you can see an interaction with the environment. You just see this. So you can, forgetting about what it is that you're actually going to be using these methods for, we want to solve PDEs on moving domains. So I'm not going to be able to do everything that I thought I was going to do because of this, my verbosity, excuse me. Anyway, doesn't matter. Gamma of t is our moving curved hypersurface, an n-dimensional hypersurface in Rn plus 1. Usually omega of t is a moving bulk domain in Rn plus 1 with a boundary gamma of t. Actually, we may view omega as being an n plus 1 dimensional flat hypersurface in Rn plus 2 with a boundary. Okay, let's say that again. If you think omega of t is our bulk domain, so let's suppose it's a ball. This ball is moving. Now we introduce another dimension, so it's a ball in R3. We introduce a fourth dimension, and of course its x4 coordinate is 0. Its x4 coordinate is 0, therefore it lies in the hypersurface x4 equals 0. It's not a hypersurface itself, it's because it's not closed in this sense. It's got a boundary. But in any case, what it is, it's a hypersurface in R4 with a moving boundary. Therefore, if we have an abstract way of describing the approximation of hypersurfaces, or the formulation of hypersurfaces, then we can do bulk equations at the same time as we do surface equations. And if we think of something process happening on the boundary of a ball linked to what's going on in the interior of the ball, we can think of that as a boundary condition. It's a strange kind of boundary condition, but it's essentially a boundary condition for the bulk PDE. And we can abstract that out, and we can find out, we can write that. So for when we're solving a coupled bulk surface reaction diffusion system, we can think of it as an abstract parabolic equation in an evolving space and look at it in exactly the same way as we look at solving a parabolic equation on a moving bulk domain. So we can, in principle, we should be able to derive a numerical methodology in the abstract setting which copes with all of this. So interface problems, we're interested where gamma separates two domains in which bulk PDEs hold. Often gamma is unknown, so we might call those unknown boundary problems. Sometimes we say free and moving when gamma changes, but essentially what we mean by free and moving is that we normally are interested in the situation when gamma is unknown. If the surface carries energy, and we wish to model the surface, the interface, or whatever it is, as a hypersurface, but we want to be associate with it an energy density, then we're all automatically led, not just to describing the surface geometrically, we're automatically led to the physics leading to geometric quantities. Because the first variation of the area functional, so the area function is just the energy when the energy density is 1. Then the first variation of the area functional leads to the mean curvature. So we're automatically led, when we're looking at energetic surfaces, we're led to geometric concepts, even if we're not describing the surface. So we're interested in coupling equations for and on a surface to equations in the bulk. So we can think of there being two types of model problems. One where we wish to approximate gamma, no matter what gamma is, no matter what the model for gamma is, we wish to approximate gamma. So the simplest model for that would be motion by mean curvature. We wish to find the domain in which we're going to solve the PDE. The other model problem would be, on the domain, we have a partial differential equation which we wish to solve. Of course, in complicated models, these two things are coupled together. Nevertheless, as a mathematician, you might wish to decouple these two things and look at, because it's easier to consider either one of those two situations and then maybe get a mathematical theory for that. You might be able to get a mathematical theory for the coupling, but when we're doing numerical analysis, we may only be able to do numerical analysis for the model problems. The point of doing numerical analysis on model problems is it gives us insight into numerical methods. It gives us insight into the behavior of discretization, and it gives us insight into what we expect from our computations for our complicated models. So this is what numerical analysts and mathematical analysts do. Oh, of course, as we saw in this picture here, we have free boundaries on a free boundary. The surface is unknown, but on the surface there are some lines. These lines are unknown. So we have a free boundary on a free boundary. This is kind of not what you normally would expect. If you have a surface on which there is a nonlinear partial differential equation, if it's an interesting partial differential equation, there's going to be regions in which the solution of the partial differential equation changes somehow, dramatically. Where it changes dramatically, somehow often we approximate it by free boundaries or interfaces. So you're automatically led to free boundaries on free boundaries once you start looking at the coupling of surface equations to bulk equations. So, this is going to be all philosophy, this talk, I can just see. Sorry about that. Anyway, never mind. What is modern numerical analysis? What is involved? Let's face it, this meeting so far has been a meeting of minds between experimental biologists, I think experimental biologists. What is a biologist is it's not easy for me to understand. And mathematical modelers who use physics to give insight into the experiments, but not so much with respect to, there's not been much mathematical analysis or numerical analysis. Now the mathematical modelers have to face the fact that there has been a tremendous improvement in computing. So large-scale computing is possible. So large-scale, it being possible, coupled with all this intellectual energy which is being spent by people working in mathematical analysis and numerical analysis in looking at complicated nonlinear partial differential equations and their approximation. That should be exploited. So mathematical modeling is not just using the mathematics of 20, 30 years ago. It's also about realizing that large-scale computing is important in mathematical modeling. So you don't have to restrict yourself to one space dimension. You don't have to restrict yourself to the Laplace's equation on a box. You need to take advantage. So that means there's a responsibility on biologists and mathematical modelers to find out what's going on in mathematical and numerical analysis. And of course, the responsibility goes the other way. If numerical analysts really think they should be motivated to do solve complicated problems because they think it's going to be of interest to scientists, then they have a responsibility to communicate to the scientists. I have to say, there's a lot of mathematics associated with looking at problems in curved domains. It's a big step. If people are having difficulty with the finite element method for solving a Poisson equation in a box and multiplying by an equation by a test function, integrating by parts using a Glerkin approximation, and and then asking the question whether which Sobolev space should I use because the partial differential equation is fourth order rather than second order, and finding out that you can't use Lagrangian conforming finite elements for solving the biharmonic equation. It's tough. It's tough to communicate how you're going to do that for solving fourth order geometric equations on curved domains, curved surfaces. So you just have to accept that there's going to be a big gap there, but nevertheless I think it's important to communicate that there are methods for solving such problems. So anyway, so in modern numerical, I think it's I gave a talk to the conference in numerical analysis. There's a biennial conference in Scotland in numerical analysis, and this conference tends to be this is another method for solving AX equals B. This is a matrix problem. Here's another method for solving AX equals lambda x. That's the eigenvalue problem. Here's another method for minimizing f of x. Of course, I'm exaggerating. Here's another method for solving partial differential equations. So we're going to be, let's look at the discontinuous Glerkin method for solving advection diffusion equations, etc., etc. And they tend not to kind of see what the interface is between numerical analysis and physics or biology or socioeconomic sciences, whatever it is. And I think that's a mistake on in their community. So this overhead was designed to speak to the numerical analysis community, which also could be used to design to speak to the, to the mathematical modeling community. So, there is, of course, as I think Philip said in the lecture, there's a kind of, you might want to start, I don't know where you're going to start. You might, you might start in any one of these places. And why I say that is because you always go round and round and round, basically. You go round and round. So let's just start here. You start with mathematical modeling. So your mathematical modeling, you've got to take into account what's available in the mathematical analysis and numerical analysis. You formulate some partial differential equations. And what I want to say here is how you formulate the partial differential equations is going to influence how you do the analysis, how you develop the numerical method, how you do the analysis of discretization, how you do the solution, and how you implement. So in our context, the question is, how do we describe the surface or the domain? Do we use a parametric approach? Do we use an implicit approach? Do we use a phase field or diffuse interface approach? We can use all three approaches. We can choose any one of those approaches. They have a huge consequence for all the way down here. At the end of the day, of course, what we want to do is to simulate. And simulate, I mean, you can simulate without responsibility, which means which is what I do, basically. I have my mathematical models, and I compute the solutions, and I compute the solutions of the mathematical model, and show that the solutions of my numerical solutions are close to the, actually approximate the mathematical model. But then you might have a responsibility to relate that to experiments. And then you may need parameter identification, which is in its own right will involve all of this. For parameter identification, you might have to solve your mathematical model lots and lots of times in order to identify the parameters. Eventually you might want to predict, and at the end of the day, in engineering, we're controlling. And this, of course, is this control part is actually the most controversial part of all. I mean, we're kind of quite happy to control whether an aeroplane lands or not. You're quite happy to control lots of engineering processes, industrial processes. You may not be so happy to control things in socioeconomic sciences. You may not be so happy how to use Google searches to control. But anyway, that's the end of the day. There are huge ethical questions associated with control. And this is obviously important in the biological sciences, which I choose to mention. So the aims of numerical analysis in this context, I want to develop numerical methodologies for interface and free boundary problems involving surface and bulk PDEs. And based on discretization of fit-for-purpose PDE formulations, what do I mean? Well, you know, people have different purposes, and that might depend upon the application. But it might also depend upon the available software, and it might also depend upon the available experience. So there can't be one best method in particular circumstances. The particular circumstances might be that your team has developed a phase field software. You've got all this experience. So if that's what you've got, well, you should maybe try to exploit it. And available understanding. Of course, this changes, but in any case, as a numerical analyst, you back off from that, and possibly it's not a bad idea not to own and get emotionally involved in a method. Right? I think it's something that I've learned. Don't get emotionally involved in thinking that I've invested my PhD and my postdoc into phase field methods. They've got to be the best because I've invested all that time, and then you come along to and you find out, oh gosh, surface finite elements, they're pretty cool. And then there's a couple, I better find a way of knocking surface finite elements because I've got this allegiance to phase field. It's probably not a good idea to get emotionally invested in methods. So we just take a dispassionate view to methods. You can't do everything in mathematical analysis. It's just too difficult for the kind of problems that people want to solve. we saw in Robert Nurnberg's talk, he was tackling a quite difficult problem. He was tackling two-phase Navier-Stokes with complicated interface conditions. He was associated with the interface between two fluids, the surface energy of the drop. And in the first instance, there was the surface energy density was 1. He mentioned the fact that the surface energy density could depend upon the surfactant concentration, and he's done work on that. And he also he has done work, and I think he mentioned the surface energy density can depend on a bending. It could be a bending energy. And he also wanted to solve fluid equations on the surface. Well, nobody has the existence and uniqueness theorems for these types of problems are only just beginning, emerging. And when they do emerge, they're not necessarily in a way which is going to lead to the mathematical formulation is not necessarily there to give a good numerical method. Nevertheless, what he did was to derive variational formulations of the partial differential equations, and he derived a discretization which was consistent with a variational formulation. And if you were to assume that the solution of the partial differential equations exist, and the calculations that you're going to, formal calculations that you do mathematically, you would be led to conservation laws and to energy dissipation laws. And what you would like, the first thing that you might like from a numerical method is that the solution of your numerical method enjoys those properties. And that's what we mean by consistent and stable to the discrete energy inequalities. And that usually is possible for complex nonlinear systems. Well, it's possible if you're sufficiently clever and you're interested in doing that. And in Robert's work with John Barrett and Harold Garth, that's what he did. He showed that for the numerical methods that he presented, that they were consistent, they were associated with a variational formulation, there was almost no ad hocery. There's a lot of ad hocery in numerical simulation of fluid problems by level set methods and other kind of volume in fluid methods. But the way that he formulated, there's no ad hocery, and he was able to show that his numerical schemes enjoyed some energy inequalities, which mimic the energy inequalities that your putative solutions of the nonlinear system satisfy. And then he illustrated by simulating, which from the experimental perspective was simple, but actually from the mathematical perspective complicated, that is simple but significant model problems. And what you can do is to carry out error analysis of the model core problems. And what we mean by that is, for example, error analysis would mean that you would really like to show that if you were to refine your discretization, that the solution of your discretization converges to the solution of of your problem. So you can do that a priori, and that's what a large amount of numerical analysis has been devoted to. Doing a priori numerical analysis is to prove error bands between the solution of the PDE and the solution of that which you compute. But you can also do a posteriori, an a posteriori error estimation, which has some ad hocery about it, but there are some rigorous results, is used to refine your approximation where it needs to be refined. So in the engineering literature, you will find a massive amount on adaptive finite element methods. So in engineering literature, the computational mechanics literature it's a good place to look for thinking about solving biological problems. Oh, I had a look at the time. Okay, so we're interested in solving partial differential equations like this. That's the reaction diffusion equation, and it's holding on a surface. The surface is gamma. There's our diffusion, there's our interaction, that's our reaction. It's a mathematical way of writing it. And here we have to understand these objects. This is a material derivative given with a velocity field v. That's the surface divergence of the velocity. This accounts for the this accounts for the local shrinking or expansion of the surface. It's what somebody said yesterday or the day before. It's the dilution effect in that one-dimensional equation, which is written down in one of the talks. Was it his first one yesterday morning? Maybe. Of course, there's some strange things here. There's this dot, material derivative. It's not that easy to think what that dot is, actually, if you're living in curved space. And if you're living in curved space, it's not that easy to think about what it is. What is the surface gradient and what's the surface divergence? Nevertheless, we do it. So the surface gradient is this. We imagine that our surface variable, which only lies on gamma, can be extended everywhere. If we're going to be extended everywhere, we can calculate the usual gradient. Then we subtract off its normal component, and then we get a vector called the surface gradient, the tangential gradient. And you notice that if this is a two-dimensional surface in 3 space dimensions, then the surface gradient has got 3 components. Okay. That is the definition of the surface gradient. It's very useful. It allows us to do all sorts of computations, analytic computations, but it also allows us to do numerical computations.
Is nu an outer product?
Nu is, sorry, no, this is, nu is the normal. This is just saying this is the normal derivative of A. Grad AI dot nu. There's no outer product there. This is the scalar product between this one and this.
Before that second nu.
Yeah, we can put a parenthesis here and one there. That's where it should have been. Yeah, thank you. Yeah. So nevertheless, this object only depends upon the values of A on the surface. So we can take that as our understanding of the surface gradient. And then that gives us a surface divergence, and that gives us the surface Laplacian. Taking the same approach, we extend A off the surface, and then we can compute its usual derivatives, this one and this, and then we call that the material derivative. But of course, if we're living on the surface, then it doesn't have this derivative, and it doesn't have that derivative, because it's living in curved space, and the space is changing in time. These derivatives don't exist. They only exist on the extension. So when you do this abstractly, you have to we'll have to work a bit to abstract that out, to work out what the anyway. That's let me not talk about that. Okay, so here's a geometric evolution law, which basically has a number of different elements. It has bending, surface tension, and it has a protrusion, it has a pressure term. At the end of the day, we have an equation like this. So this is now we want to find gamma. Gamma is a function, gamma depends upon time. This is comes from the Helfrich energy or Wilmore energy. This is the surface tension. This is like motion by mean curvature. If we just drop all of this. This can be used to maintain volume. This is, this term we have to solve on the surface. We have to solve a system of partial differential equations. So it could be a target. I'm not going to talk about the biological significance of this. I'm just going to say this could be a mathematical model which arises in biology, which is quite complicated, and we would like to develop a surface finite element method for solving that. So what do we need? We need some concepts in geometric analysis. We need some analysis for PDEs on evolving domains in order to be able to formulate the problem, and then we have some numerical analysis. Okay, so what is a shape? So here's the two shapes. Here's two shapes. So let's now just imagine this one here is representing a volume. Okay. So what is a shape? This one, I've taken part of the surface of this, cut out the interior. So basically, this is a part of a two-dimensional hypersurface in 3D with a boundary. Okay. So it's called a submanifold. If we think of this as, think of the whole domain here, we think of this as a hypersurface, flat hypersurface in R4 with a boundary. But let's just consider it as a bulk domain to begin with. So what is the shape? So think about n equals 1, 2, and 3. So omega contain Rn plus 1 is a bounded open set. And let's suppose that gamma is its boundary. So how do we describe omega? Because if we want to approximate omega, we're going to have to describe it, right? Well, you can approximate it by you can describe it by an indicator function. So an indicator function is a map from Rn plus 1 to 0 and 1. I'm not being very precise. You might think I'm being over precise, but I'm not being that precise. Omega is those x in Rn plus 1 so that this characteristic function is 1. Omega takes the value 0. I hope that this is going to be an open set. It might not be. I've got to define these things a bit better. It's an indicator function. That could be a description. People wanted to solve PDEs in complicated domains a very long time ago because they wanted to develop explosives and things, and so they had lots of computational fluid dynamics in computational domains, and because people had finite difference technology, they worked on square grids, and so they describe domains by indicator functions. So you have a square grid. Your indicator function is given a value 1 and 0. So all the grid points, the indicator function is either 1 or 0. And this gives, then you're led to, you have to somehow, that's what you try to calculate, some sense, and then you have to calculate how much fluid there is in each one of those cells. And that's volume in that's typical. This method is still used. Method is kind of in legacy software, and that's why it's still used. But there it is. You can use that method. You can use a level set function. So in this case, we suppose that we have a phi, and we set omega to be, it's continuous, and we set omega to be the region in which phi is less than 0. So this has more information because phi is continuous. There's more information. Phi is continuous. So now we have got plus, 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 minus, 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 minus. There's more information because I've got a value here and I've got a value here. So in principle I can interpolate. So hopefully, ooh, that's a problem. Oh gosh, well anyway, maybe I can, oh no, that's not down there. So I can interpolate, presumably, do some numerical interpolation. And now what's my problem? This is a level set method. My problem is that if I'm solving a geometric equation, maybe I can make this fly without doing, there are still things that you need to do to make it fly, by the way. But if I'm solving a PDE in the bulk domain, or PDE on the surface, so this is my interface, So I wanted to still a PDE in here and a PDE here. There, my description of the domain in which the bulk domain in which the PDE holds is kind of not a uniform, it is not a union of square. So I've got, it's kind of an unfitted. And you can do this with finite elements as well. So if you're led to a level set way of describing the evolution of an interface, often you're led to unfitted finite elements. And if you go back to Robert Nurnberg's talk, he used this also occurs if you use a parametric description of the surface. Suppose somehow or other I compute my interface by surface finite elements, but I have an equation in a bulk on either side of the interface. So I might have an absolutely wonderful expression, wonderful approximation. I might even know it exactly, this interface, and it's moving through. I'm led to using unfitted finite elements for solving the equation in the bulk domain. And this is what Robert did in his talk. He used unfitted finite elements. Okay. Yeah, so we had a description of a hypersurface just by taking, say, the zero-level set of phi. If we wanted to define that properly, we would also want it to have a normal. So we don't want gamma to have an interior. There are interesting problems when your level set function develops an interior, in the sense that the region in which phi is identically 0 has non-zero measure. And that leads to it's something that you might want to avoid. Okay, so of course all these can be time-dependent functions to give evolving domains. So indicator function is you led to one description, a level set function, a one numerical method. Level set function you led to a numerical method. The fact that you've chosen your way of describing your surface, I haven't told you how you compute the indicator function or how you compute a level set function, but once you've chosen, that's the way that you're going to approximate your surface. You're led to some difficulties or questions with respect into solving the PDEs, both on the surface, okay, or away from the surface. And these are questions which exercise computational mathematicians and numerical analysts. Yeah, so this is a moving hypersurface without boundary. And we say if the normal varies in space, then the this is not what we do not say this. If the normal varies in space, then we say the hypersurface is curved, otherwise it is flat. If the normal is constant, then it's flat. And we get the curvature from calculating the derivatives of the normal. Okay, we take the matrix of first derivatives of the normal, and we take the trace, and then we get the mean curvature. And we can describe a hypersurface with a boundary. We might describe it with two level set functions. One to define a hypersurface gamma wave, a non-gamma wave. We have another level set function, and that can be used to describe the boundary of a submanifold gamma. Okay. And I'm just saying again here, this is an example of a flat moving hypersurface with boundary. Basically, we describe our flat hypersurface through xn plus 1 equals 0, and we define its boundary by using a level set function phi on the surface. There's our tangential gradient. So one thing that's interesting, the integration by parts on a curved surface, well, integration by parts on a hypersurface, gives us this formula here. And we should be aware of that we get the mean curvature vector coming out here. So this is always important when we're doing calculations. And another interesting thing is that if we take the mean curvature vector, multiply it by a test function, then what we get is basically the Laplace Beltrami of the identity operator. And this is a very useful way in doing surface finite elements. This identity, when it's put into the framework of discrete surfaces, gives us a way of computing a mean curvature vector. And that's exploited in solving geometric equations.
Is mu an indicator function, right?
Sorry?
Is mu an indicator function?
So where am I looking?
The second line from the bottom. The second.
No, it's identity.
Mu.
U, is it U? I don't, oh, what is, oh, this mu.
Yeah.
Oh, I'm so sorry. Yeah, mu, sorry. Mu is the conormal. So mu is parallel to the surface, gamma, but it's normal to its boundary. Okay. That's in a flat domain, we can call the normal. But we're living in a curved domain. So so this is one of the slides of a 256 slide lecture course given to graduate students on surface finite elements. I don't expect you to read it. That's just, if we really want to get down to doing surface finite elements or PDEs on surfaces, then we would have to spend some time studying. Okay. And we begin by, we don't need to read this, except I'll just point out that you have, that we wanted to, we would like to talk about parameterized surfaces. So we have some definitions of an n-dimensional parameterized CK surface. We have a definition of a local parameterization, and then we can define functions which are differentiable. And basically, the idea is we have a flat domain somewhere. We have a flat domain somewhere. And we have our hypersurface over here, and we have a map from our flat domain to our hypersurface, and we describe this. We have a parameter. That's our parameterization. Okay. So when we talk about differentiation, we talk about differentiation with respect to the parameter over here. Okay, so then we can talk about tangent spaces, and using these parameterizations, we saw a little bit of this in Alan Gradia's talk. We saw the GIJs there, I think, briefly. So we have, so the formula for the Laplace-Beltrami operator is like this, and there's the tangential gradient. Well, when we're doing calculations, analytic calculations, sometimes these formulae are useful. When I'm doing the numerical analysis with the numerical method with surface finite elements, we don't use this. Okay. So this is the matrix of first derivatives. This is a surface derivative. That's its tangent. It's the ith component of the tangential gradient. And if we consider this map here, mu is an eigenvector with 0 eigenvalue, and then if we take the trace of this, then we get the mean curvature. So I usually mean the mean curvature is the sum of the principal curvatures, rather than the average value, the mean value. So we have parameterized hypersurface, but I also showed you how you would describe, it's easier to think of describing a hypersurface by a level set function. Well, they can be shown to be equivalent. So in certain circumstances, then our parameterized surface and our hypersurface defined by a level set function are equivalent. We're talking about the same things. And if we use tangential gradients, then we are led to this projection operator. And this projection operator might be useful in implementing numerical methods. Okay. All right, so fitted versus unfitted finite elements. This is our domain. This is a fitted triangulation. This is an unfitted triangulation. And we can see that this is the finite element version of fitted unfitted. And I would like to argue the merits of using fitted finite elements here in this time remaining, but I've also worked on unfitted finite elements. So you triangulate, this is a bulk domain, you triangulate it, there's a refined triangulation, and you notice that this triangulation, this bulk domain has faces on the boundary. It has a face on the boundary, which is a triangle. So if you're solving a coupled surface bulk equation, then it would be natural to define your you have a discretization of both the surface and the boundary. So it would be natural to have a finite element space in the bulk with a trace which defines on the boundary a good finite element space for solving the PDE on the surface. Of course, there are constraints here. Whether if you've got a fourth order equation on the surface and a second order equation in the domain, in the bulk domain, then you might have a problem. If you're using Lagrangian finite, there's problems to do with whether your finite element space is going to live in the right spaces to make the discretization work. So that's where you have to do some numerical analysis. Not everything was going to work. So here is these are interpolated surfaces. So this is a time evolution of a surface. That's the time evolution of the same surface. Each of these is an interpolation. The triangulations are exact in the sense that the vertices of the triangles lie on the surface. And so we can notice differences between them. We see you might prefer this triangulation to this one. You see, with this triangulation, the elements are roughly similar size throughout the surface. This one, there seems to be some coarse elements here and some elements here. We don't know. There is an issue. This triangulation was obtained by moving the vertices of these triangles in the normal direction. These vertices were moved in a different way. They lead to different triangulations. Yes?
What's the underlying evolution equation?
There's no evolution equation. It's a formula for this is a formula given by a level set function, and all I've done is to define the mesh. This mesh, these points are given by the normal velocity, if you like. These are given by a different velocity. They give different triangulations. We want to solve a PDE on the surface of this, maybe. So your PDE, your numerical method for solving the PDE would like to have a good mesh. So there's an issue about how you would have, there are issues, anyway, not could be, there are issues about what should the mesh be on this evolution. Should you move the mesh in the normal direction? Well, the answer to is it might be the only method you've got, but it's not necessarily a good method. Going back to Robert's talk, Robert Nurnberg's talk, he said in his talk that he has a method for inducing tangential motion of the vertices so that he gets a good mesh. That's what he said. And it's true, he has a good mesh, and so that's one of the significant contributions of Barrett, Gark, and Nurnberg. It's an issue. Okay, so it's something that needs to be addressed, mesh generation. Now suppose that you have a mesh. Here in this evolution here, we'll show you, this is a two-phase geometric biomembrane. And the idea here is that we have to find the surface, we have to find the vertices of the triangles, and we also have to solve a parabolic equation on the surface simultaneously. And so there's the initial mesh. The color coding is an indicator that we're solving a kind of an interface problem on the surface. It's an Allen-Carn equation. Basically, it's a relaxation of a Ginzburg-Landau equation, Ginzburg-Landau energy on the surface. So, let's suppose we're using piecewise linear finite elements. So the surface is described by piecewise linear function, which means that we're computing some xj's of t's, which are the location of the vertices. Means our surface, in some sense, xj of t chi j. I have to be careful what I mean by chi j, but chi j is a finite element function. It's 1 at the vertex of a triangle, it's 0 at all the other vertices of the triangle. So this is j, and the finite element function is 1 here, and it's 0 at all other vertices. It's a piecewise linear function. And that's a description of the surface. Meanwhile, on the surface, we want to solve an equation for surface variables. Well, let's call it alpha. So these could be the values which are supposed to be approximate the solution of a reaction diffusion system. And we want to compute those. As time evolves, of course, then everything is changing, and that's what we do. And we need to we need to describe how we're going to do that. And so this is the evolution, and that's what we're doing. In this particular setting, there is an interface between the red region and the blue region, and this is an approximation of this geometric biomembrane problem. There's a different spontaneous curvature in the blue region to the red region, and there's a line energy associated with the zero-level set of this solution of this Allen-Carn equation. Basically, this is an approximation of solving gradient flow for a Helfrich type energy with a spontaneous curvature, with a line energy on the surface which carries energy. And in the sharp interface setting, it means it's for the surface itself, we've got a fourth order geometric evolution equation, and on the surface there is another free boundary which is solving some kind of geodesic curvature flow. That's the kind of thing that we would like to do. Of course, what we would like to do is to do this and also solve a PDE in the interior and the exterior. Okay. Just now relating to, I think, talk yesterday, this is what, if you use a phase field method, then you're replacing your sharp interface by a diffuse interface. Underlying this is the notion that you'd like to solve the problem on a fixed mesh. And you would like to solve the problem on a fixed mesh. But you've got this, because you want to solve bulk equations here and here. You want to solve the Navier-Stokes equations here, we want to solve the Navier-Stokes equations here. This is a cartoon. This is not the mesh that we used in the simulation. It's just exaggerated to show the kind of thing that one does. So when you're using a phase field, of course, you could have used this grid, this mesh here, and refined it everywhere. But that kind of crazy, because you use this phase field method, and you've got need a fine mesh because you're using a phase field. But why you don't need a fine mesh to solve the Navier-Stokes equations, possibly. Okay, so you've got this your game is you want to use an underlying fixed grid. So the natural thing you're going to do is to use time-dependent adaptivity. So you refine and coarsen in appropriate places, and this is what you do. So there, the underlying grid is fixed, but you refine and coarsen as you solve the phase field equation. Okay, so In this instance, this is what we call the sharp diffuse interface front tracking, because we use a different type of phase field. Yes, please. Yeah. Okay. So I did say that one of the interesting things is to find a PDE method to calculate a grid. As you see, I've got nowhere in this talk, but I kind of was thinking when I was asked to talk at an ASI, I thought that I might have 2 or 3 lectures to to speak. Anyway, this is a problem in a flat domain. We're solving a partial differential. This is our evolving bulk domain, and we're solving a free boundary. It's a moving boundary problem. And we're going to calculate, we have a method for calculating the nodes of the triangulation, which is geometric in nature. In fact, this triangulation is obtained by computing on half a sphere. We have a discretization on half a sphere, and the idea is what we want to do is we want to get something which is a mesh which looks like it's conforming. We're interested in computing approximations to conformal maps. And what you see here is that the mesh quality, as measured by the ratio of the inscribed circle to the circumscribed circle, is pretty much constant in this simulation. The idea being is that's a good quality for a mesh. And this is, oh, sorry, I should. Oh, okay. And this is what, so we're solving in here. This is a beautiful evolution of the mesh. We're solving the only velocity which is physical is on the boundary of the domain. We extend it by a harmonic map into the interior, but that's not the boundary. Does not give the velocity of the nodes. We then compute another transformation to give the velocity of the nodes. But if we'd use the velocity, sort of this induced material velocity by using Laplace's equation to compute the velocity components in the interior given the normal velocity on the boundary, we would have got a bad mesh. But we use a geometric approach to computing a good mesh. This is recent work, and it is far more involved than and I just wanted to actually show some pictures here in the few minutes that I've got. I started I started a little bit late.
No, that's why you've got a few minutes.
So here is what you might, I'm going to talk a little bit about two-phase geometric biological membranes. Here's the energy. We've seen this energy a number of times. We add to this, I'm going to ignore the Gaussian curvature for reasons which have been explained once or twice. We introduce a spontaneous curvature. The idea is the spontaneous curvature can take 2 values, one associated with the blue region, one associated with the red region. Associated with the boundary between the blue and red, we have a line energy. And I want to compute minima of this energy. And the idea is that we're going to approximate this. We're going to use a sharp description of the surface. But on the surface, I'm going to use a Ginzburg-Landau energy to approximate the line energy. So there's a phase field equation on an evolving phase field equation on the surface. And the idea is we're going to do relaxation. We're going to do gradient flow. So there's going to be a geometric evolution law for the membrane surface coupled to a parabolic equation for the equation on the surface. And in this evolution here, you see that we have these 3 red components, and the evolution is slow. And there's a the timescales here are not physical timescales, but we can see that we get this evolution to the surface. This is a triangulate. This is done on a triangulated surface phase field. Okay. So that was the energy that we compute. There's our phase field. There's our way our spontaneous curvature depends upon this value of C. A C essentially takes two values with a diffuse interface. And you can see why it's difficult to write down lots of equations, because they can rapidly become very complicated. But this is the first variation of these integrals, and we led to expressions like this. In the end of the day, we led to coupled equations like this. This is the geometric evolutionary law for the surface. This is the parabolic equation. The only thing I want you to take away from here is this, that here it's complicated by the fact that the spontaneous curvature depends upon the concentration. But there it is. That's what it is. You can do formal asymptotics in the on stationary solutions, and you can recover limiting problems which define this surface. Seen this? Sometimes you have to do remeshing. Okay, so this is a complicated surface. You have to do some remeshing. You have to do some adaptivity. You should be responsible in showing that your approach has some convergence. If you're using phase field, there's an epsilon parameter. You're converging to some kind of sharp interface problem. So here is some results which show that we try to be responsible and show that we get convergence in epsilon. And this is the convergence. This is where the neck, this is where this location of this line should be, and this is the computations. Another way of being responsible is we compared our numerical simulations with the solutions of ordinary differential equations in this axisymmetric case carried out by Ulica and Lipowski in '96, and our computations agree. Nevertheless, we can solve with so you might say, why use finite elements? Well, we can compute non-axisymmetric shapes. This is our initial configuration. This is not accessible to formulae. You can use this to look at phase diagrams. So this is the membrane energy against a surface tension parameter, and you can get local minima coexisting. And in this instance, the one on the red curve has lowest energy. This dotted line has lowest energy, and here this red curve ceases to exist. And these are the kind of shapes that you get. And then you can compute multiple RAF equilibria. And for those of you who got sharp, who've been observant either in your accommodation or within the institute, would have seen this wallpaper on the cover of one of these brochures that the Newton Institute produced. This is associated with the Free Boundary Conference. And that's the mesh. That's what the final mesh would be for multiple raft equilibria. And you can compute all sorts of other shapes, and you can get, as I said, you can look at phase diagrams. These were obtained by surface finite elements, and I'm going to find, hopefully. Oh, I wanted to yes, we should look at this one. These are cute computations done by Shaker using our ALE type approach, and the evolution equation for the surface in each one is different, but they're solving a parabolic system of interaction diffusion equations on that curve. Okay, so let me just. And this is how it would look in 3 space dimensions, and the protrusions occur when the solution of the interaction diffusion equation, one of the components, is large. This is our cartoon of an object which is moving and knocking away. And again, the point is that this is solved on the surface. It's not solved by phase field, it's solved on the surface. There are some, and here is our chemotactic thing. all of these are moving. There is the interaction between the two cells is they don't intersect because of some kind of repulsive potential. The only thing I wanted to these are cartoons. But the point of the cartoon is to say that you can solve PDEs on complicated surfaces with changing time, and if you put better biology into them, then you can do better with respect to simulation real things. And I want to go to my final. You can see there's a lot of stuff here, and I've lost it. Okay, all right. So the outlook is the coupling of evolving manifolds and submanifolds of differing dimensions. We've seen, look, you saw last week, you saw this bulk nucleus, you saw this sheet coming off it, which is, people like to think, and then out of the sheet emerge these philopodia. That's what I saw. I mean, I know I saw all sorts of other things. That is, I saw a bulk three-dimensional domain connected to a sheet connected to lines. That's coupling of evolving manifolds and submanifolds of different dimension. That's what that means. It means solving PDEs on that whole system together. Well, we will be able to do that. In the end of the day, we will be doing it using surface finite elements. We won't be using because they're going to be more efficient. But it will require some sophistication. So that's the fitting of evolving triangulations of coupled evolving manifolds. We need to understand how to do this for evolving finite element spaces, so all of the things mesh together. Of course, we need to have good variational formulations. You need this coupling of the evolution of the manifold to the PDE on the manifold. And we've got to generate meshes. But it may very well be that the way mesh generation will go, we will use partial differential equations to compute the meshes. You could try to do all of the above for unfitted finite element method, diffuse domains, and hybrid approaches. A hybrid approach is what I meant by here, where you use a sharp method for computing the interface coupled with unfitted finite elements for doing bulk. And from the lessons for the numerical analysts is, as I learnt this week, when we should be providing user, and in this instance, biological modeler friendly computational tools. So that's where I'll stop. Thank you.
I know there'll be a lot of questions, and
yeah,
we have a tea break, which we can go into by a few minutes. On the other hand, you can also ask questions at the tea break. So what are the most urgent questions for this intriguing presentation? Everyone's asleep? No.
I actually have a question to this multi-domain. I mean, so basically, is this a stable shape what you got in the, the one which is red and blue where you have multi-raft?
Yes.
This is a stable minimum?
Yes.
Stabilized by the fact that you have the spontaneous curvature?
Yes. Well, what do I mean? What do I mean by it being stable? I mean that at the time that we did this 3 or 4 years ago. At that time, it's stable meant that we computed we minimized this functional, and we got to an approximate steady state. The velocities that we were computing were 10 to the minus some small number. So, when that happens, you tend to think that you've got a local minimizer. You can't say that you have a global minimizer, but one might think that one has a local minimizer. Excuse me?
So changing the number.
So it's a local minima, yeah.
Yeah, so that is for sure true. That I understand. But my question.
Whether it's a global minimizer, I don't know whether it's a global minimizer because we didn't explore the whole space. But actually, I was more interested at that time of getting that of obtaining that picture. Right? I was interested in this. So I was more I was quite happy to get the cartoon. I mean, well, this is a mathematical model. I mean, it's a kind of a reasonable mathematical model proposed by Ulrika Lipowski. I was more interested in obtaining that picture there, which may very well be a local minimizer, or it may even be some kind of metastable state where there is something in there which is going to take it to something else. But on a time scale, but by some mechanism which I don't know. All I can tell you is that the mathematical model that that I presented appears, from the numerical perspective, to have a local minimizer with that morphology. I can't say anything more than that. Yeah.
Time for one more question.
So what you show is mostly problems in which the surface evolution is led by diffusion-dominated problems.
Yes.
Did you have a look in problems in which advection could be dominant in a way? And because on flat surfaces there is all the question of upwinding the schemes and so on. It's been a lot of work. So
you're asking the question that if your partial differential equation on the surface has advection,
yes,
how would you approach the solution of the surface partial differential equation? Okay, so we have my colleague Andreas Dedner has had a PhD student who has looked at this problem on stationary surfaces, and he's looked at discontinuous Galerkin methods. So the idea here is that there is technology for solving in the flat space these types of types of things, and then to try to transfer that mathematical and numerical technology to PDEs on surfaces. And the first start for that has been the analysis of the discontinuous Galerkin method. As far as solving the problems on a moving domain, I have not looked at getting good methods, or whatever they might be, for advection-dominated transport problems on the surface. And of course, that's going to be important in the surfactant problem, where the diffusivity is very small. Yeah, it's going to be important. But my suspicion is that the kind of methods which are available for the flat case will also work on the curved surface. But you have to take into account the changes in the geometry, and there is some technical issues associated with that. Yeah.
I would like to know your opinion about meshless methods, because
About what, sorry?
meshless methods, they are numerical models that normally try to remove the dependency of the mesh.
Oh, meshless methods.
What do you think? Do you think that in the future we are going to be able, because normally we depend on the mesh, so we need to discretize and to modify that.
I don't know anything about meshless methods.
And do you think in the future we are going to be dependent on the mesh?
I'm happy to be dependent on the mesh. Which gives me a living. Sorry, I know that's a facetious answer. I mean, I don't know the answer. I don't know the anscer. I always think that when you have a bright idea, and meshless methods are a bright idea, at the end of the day, when you come down to implementing and actually go into the technical details, you find the issues that arise in other methods will arise in this method in a slightly in a different way. So that's my experience.
Okay, let's break. We need to get back to the minute or two before 11.